Everybody. Welcome to the Frosty Drew Observatory and Science Center Stargazing Nights Live. Again, we are all working from home tonight, and we are fighting with some clouds, but the forecast is looking a bit better than we expected. And myself and another one of the astronomers on tonight, Derek Schott, are both set up outside in either our makeshift labs or our observatory, getting ready to show you live views. Now, we're going to have passing clouds. We might even get hit with rain, so you might see us scurrying to cover things up. But we have enough images that we captured this week and images that we've captured this year to show you a lot of great stuff. Now, a few things that I want to cover first is tonight's team that's on the call is we have Derek Schott, we have Gavin Olson, and we have myself, Scott McNeil, and we are the astronomers on tonight's conference. Our moderators tonight are Sky Evangelist, Lindsay Abrams, and Jessica McNeil, which you've seen both of them if you have visited in the summer and went past the greeter station. That's usually where you'll find them freaking out. Now, we're going to start something new this week. We've been getting a lot of people that are starting to write in with questions, and instead of writing people back responses, we figure why not address some of these questions we're getting over the live chat. So if you guys have questions outside of the live stream, so during the live stream, on the right-hand side, you see the chat over there? That's the place to submit your questions. Lindsay and Jessica will take your questions, and then over the air, they'll pose your questions to us, and we'll give you answers. But during the week, if you're looking for an answer or you want something to be brought up during the live stream, then please send us an email at astronomer@frostydrew.org with your question, and we will address your question live on the live stream. Now, tonight, we actually have a question, and I'm going to dig it up real quick here. We're a little bit behind tonight, as you noticed when we started later. It's because we got the clear skies again at the last minute. We're like, hey, wait a minute, I think we can score with this. So this week we had a write-in from someone who's been on just about every week. His name is Kenneth Sebesta. And he asked, what controls a comet's orbit around the sun? Why doesn't the comet just keep going in the same direction after it passes the sun? Ken, that's an excellent question. And comets are on everybody's mind right now because we have Comet Swan, naked eye visible, coming into the sky in the northern hemisphere. Yay. Comet Atlas broke up into 4 little fragments. It now has sub-naming and sub-designations. And now we have a new comet too, Comet U6 Lemon, which could become naked eye visible over the next month also. I mean, this is awesome. So when a comet passes the sun, a comet usually spends its life either in the Oort cloud, which is about 1 light year distant from the sun, and it's the very furthest edge of the solar system. And in the Oort cloud are a lot of leftover objects from when the solar system formed. Sometimes comets get like little pieces of that leftover material gets pushed in to the solar system from events on other stars, like a coronal mass ejection on Alpha Centauri or a coronal mass ejection on Sirius. And they give a little bit of a magnetic push to these objects, just enough so they can fall into the sun's gravity well. So as they come in, they're speeding towards the sun. And they swing around the sun, they pick up a lot of speed, and then after they pass the sun, they slingshot back out. So they don't stay around the sun, and they don't just go past the sun. And this is because of the amount of gravity that the sun has. And the entire motion of the comet, period, is due to the sun's gravity. So swinging around the sun and firing back out is what most comets will do from the Oort cloud. Now, if you have a comet that's not an Oort cloud comet, or like a short period comet, a comet that has less than a 200-year orbit around the sun, a lot of these comets hang out, in between Neptune and Jupiter area. Sometimes they come from the Kuiper belt, and Neptune will kind of fling them in, and we get comets from that region. And these comets have a much wider orbit, or much more circular orbit than some of these Oort cloud comets, but it's the same thing. It's the sun's gravity. The sun's gravity is what's pulling the comets in and increasing their speed enough for them to slingshot back out in the direction they came from. And it's important to note too, as a side note to comets, when you see that comet's tail, like think about Comet Swan with that amazing ion tail. That tail is a product of the solar wind. And it's the comet encountering the solar wind, heating up and outgassing. All those volatile materials are outgassing. They're forming an atmosphere around the comet called a coma. And then they leave a debris field behind it and an ionization trail as well. Since it's a product of the stellar wind and not the comet's motion, the tail always points away from the sun. So when the comet leaves after it passes perihelion, its closest point, and starts moving back out of the solar system, it looks like it's chasing its tail. So I'm going to bring up real quick a video of Venus that we captured today. Now, Venus has been doing some amazing things right now. We've had a really excellent time with Venus, and Venus is kind of coming to an end. So this was earlier today. What you're seeing here is Venus at about 10% waning crescent. And though you probably haven't been looking closely enough, you also, if you've noticed over the last couple of weeks when we're showing you images of Venus from earlier in the week, that Venus is looking a lot larger right now. So as Venus continues to orbit around the sun and starts moving into a position called inferior conjunction, which is when it ends up in between the sun and Earth. So as that happens, we see less and less of the side of Venus that's actually in sunlight. And we see just that little tiny 10% of the sunlit area, where most of the side we see is the side that's in night. But since there's nothing to illuminate that side, it just looks dark to us. Now, as Venus continues this motion, though it's getting thinner in phase, it is getting closer to us. And that's why it looks so much bigger in the sky. Now, we have about maybe a week and a half left of good Venus viewing, because now that Venus is getting so close to inferior conjunction, in between us and the sun, it's dropping a lot lower every day on the horizon after sunset. And eventually it's going to get so low that unless you have a really excellent view or awesome view of the western horizon, you're not even going to see it anymore. We're going to continue to catalog it every day over this period as long as it's clear, until we can't safely do it anymore because it's too close to the sun. Now, this was maybe 2 hours ago today we captured this image. But I have another image I want to show you here. And this image here is a progress that Venus has been giving us over the last month and a half. So take a look here. You're looking at Venus's phase changes from April 6, 2020, all the way up to May 13th, 2020, so a couple days ago. And you'll notice that, yes, it is definitely getting thinner. The crescent is definitely waning. But more importantly, take a look at the size changes. All of these images were captured with the same telescope, the same camera, the same filters, and the same imaging train. So that means it's the same spacing in between the camera and the telescope and all the same devices. And that allows us to keep the scale the same. So these changes you see in size is not a product of processing. It's actually a product of Venus's orbit around the sun as it gets closer to us. And when we add today's image, you'll notice that there's an even larger view. And even if you look here, you got May 12th and May 13th on the right-hand side. And even between those two, there's a size difference. And it's because now that Venus is in that last leg, it's getting big really quick. So if you have any time over the next week and a half, get out and take a look at Venus. If you have binoculars, we're talking 10 by 50 binoculars, 10 by 8 or like 8 by 50s, you can look at Venus with them and you can actually see the crescent, and you can do it during the day. But if you're going to do it during the day, do it like tomorrow. Don't do it in a week because it's getting too close to the sun and you don't want to burn your eyes out of your face, right? Don't ever look at the sun with anything, nothing, except like correct solar filtering devices like solar shades. Now,
hey Scott, so Ken had another question. He's asking about planets and what holds the planets in a stable orbit around the sun, and why don't the planets take off and go somewhere else?
Ken, gravity. I feel like every time you ask a question, I'm going to be like, gravity. So it's the sun's gravity. Now you think about it, the planets are orbiting the sun, so there is definitely a centrifugal force as well, that move outward, and gravity pulls them back in. So what you have is a stable equilibrium or a stable balance. Now, when you think about planets orbiting the sun, it's not just there's something called a barycenter. And a barycenter is that center point of gravity that both the objects create. Now, the barycenter will be closer to the more massive object, in this case, the sun, but it's not at the center of the sun. It is in the case of the Earth and the sun, it's within the radius of the sun. So Earth spinning around the sun, Earth's gravity puts a little bit of a wobble into the sun. So the sun doesn't just sit in the middle with the Earth going around it. It kind of wobbles a little bit because of the Earth going around it. And that's the same with all the planets. The larger the planet or the more massive the planet, like Jupiter, the more of a wobble it puts into the sun. Now, this is where the planets formed, and this is where they will remain. Not all planets that form around the sun make the cut, though. Kind of like, down here on Earth. We got natural selection. It's not survival of the fittest. It's survival of you just barely made it. That's kind of like a star system or a planetary system. I mean, look at Jupiter. Look at all the objects in the scattered disk. These are the objects that didn't make the cut. So Earth and the other 8 planets, or 7 planets in this case, are in orbit around the sun due to the sun's gravity.
And something else interesting about Jupiter and that barycenter is Jupiter is large enough that the Sun-Jupiter barycenter is outside of the radius of the sun's surface, whereas all the other planets are within the sun's radius.
This raises questions, Derek, about Jupiter. When we get people arguing about Pluto's planetary status, but on that side, we have a pretty good understanding of what's going on. It's on the Jupiter side, the higher massive side of planets, where it gets a little murky, that designation. And when you think about all the stars in the galaxy, and you're talking at least 200 billion stars, 68% of them are binary stars. It's more than one star in the star system. So single star systems like the solar system with just one star, the sun, are less common. And Jupiter, being so close to the size of some of these ultra cool dwarf stars or brown dwarfs, raises a question: what is Jupiter, planet or star? The real smoking gun is, did Jupiter form from the protoplanetary disk or solar nebula, that leftover material from star formation when the sun formed? Or did Jupiter form from the same molecular cloud that the sun formed from? If it did, then it's a star, and we can join the more popular category of binary stars and not be such the outcast, right? But if it did form from the protoplanetary disk, then it is a planet, whether we like it or not.
Another interesting fact about Jupiter is that it emits more energy than it absorbs from the sun. One of my high school factoids.
Yeah, there's some really crazy things about Jupiter. I mean, if you think about Jupiter, it's really hot. I mean, it emits largely in infrared, but sometimes I wonder, if you turned the sun off, would you actually see Jupiter just barely squeezing in to that ultra red side of the spectrum, like right around the hydrogen alpha wavelengths? And we're trying to figure out the state of Jupiter's core. Like Earth's got a rocky core, and we got so do most of the planets, but here we got Jupiter, and the best we can tell at this point that it's like the material of cotton candy. So who knows? We're a lot to figure out with Jupiter. Now, Derek, do you have anything live yet, or?
Lining up on the first thing right now.
All right, I will show another
Lindsay,
image.
I think there was a question.
Yeah.
Fire it off, Lindsay.
Hey, so Oscar wanted to know if you guys have any pictures of comets passing Venus.
Passing Venus? No, we don't. And I don't remember any comet recently getting into the area of Venus from our point of view. So, though I do have a picture of the International Space Station passing Venus when Venus was passing the Pleiades.
Let's see it.
All right. Let me dig this up. Let me see if I can find it in here. So, and that was really quite a night, because that was somewhat unexpected. I was actually out trying to catch the conjunction of Venus and the Pleiades, and then out of nowhere, I was watching the International Space Station cruise by, and I'm like, wait a minute, that looks like it's going to crank right past the Pleiades. And hook up, I got the shot, and I couldn't believe it. And I started tweeting, and then I felt like, that social media crazy guy. So let me get this guy open real quick here. All right, so real fast. It's over. Okay, here we go. That's almost it. That's it. So here is the conjunction of Venus, the Pleiades, and the ISS. And in this image, there's, again, there's a lot to look at. So we had a lot of clouds that night, and I was fighting with the clouds trying to get a good view. And they cleared out just in time for me to capture this shot. So Venus is obviously the bright object right in the middle there. And underneath it is the Pleiades, the little open star cluster. And then right to the right, that streak in the sky you see right over here, this is the International Space Station photobombing my shot, thankfully. And this over here is actually, it's called the Hyades, which is the face of Taurus the bull. And this was a really great shot, and I was really happy to get it. And this happened right before we went into global lockdown mode. So this was back when we actually saw people's faces, right?
Super cool shot. Wow, thank
really
you.
Heard the voices.
All right. So I'm going to turn my screen over to Derek.
Uh-oh.
Okay.
You good?
Some live views.
I got one picture before we go completely live because I got to get the image captured now that things are lined up. But we can talk about this one. We'll try to do this one live later as well. So a couple nights ago, we were talking about galaxies, and we were talking about how they are very dim and some of the structures that they go through. So earlier in this week, we actually had some pretty good nights. I got some time on, let's see, sorry, rambling, trying to buy myself time here, but we switched platforms again, so I lost where the buttons go.
Yeah, you guys are all our beta testers.
Yeah. So this is the Whirlpool Galaxy, which is near the Big Dipper. Later this evening, we might try and go see some other galaxies live and see what they look like without being able to do post-processing. But this one is a very, very popular target because it is actually an ongoing galactic collision. You can see the main galaxy there in the middle, and then the dwarf satellite galaxy above it in this photo. And then there's the connecting, gas trail that looks like, another arm from the main galaxy. And this picture is all monochrome, no color, just, light coming into the telescope, and then the picture presented here. So this one is, if you're looking at the Big Dipper, it's at the end of the arm, or at the end of the handle, the last star, and then you kind of go 90 degrees back down towards the bowl of the Dipper. Yes. M101 is the other way. They kind of make this triangle, which is kind of neat. So let me transfer over the first picture we got from the live telescope over here, which is going to be the Beehive cluster. So it's a little clumsy. We're still trying to figure out the exact mechanics of doing live for various telescopes.
And weather hasn't been helping us figure that out.
And weather has not been helping us figure that out. Unfortunately, a lot of our, my astronomy laptop is not the most recent thing in the world. So it can't handle doing any live streaming. So I have to capture
I have a live view now if you want me to grab something real quick.
Yeah, if the clouds have cleared for you, let's go do that. And then we'll come back to me when I've got this thing lined up.
So at the moment, we actually have an actual view, right? I mean, that's I feel like that's just a rarity on a Friday night right now. And now I'm going to switch over to my phone, which is currently plugged into my telescope here. And in the view here, we have the binary star Gamma Leo. Now, Gamma Leo is about 164 light years distant from us. And this is a true binary star system. So what you're seeing here is actually two stars right next to each other. Now, it's going to be a little tough to see them because they're quite close, but you'll notice that it looks a little elongated, and at times it actually looks like you can actually see the two stars. These stars, gravity keeps them together. Now, this is like planets like we were talking about before, but in this case, both of these stars are working together. And these stars are orbiting around that center point of gravity called a barycenter. So essentially they orbit each other. And a good way to think about this is if you were there, living there, like on a planet, you would have two suns in the sky. And that could make a dark night rather uncommon. So at this magnification with the phone, I'm not getting the best distinction between the two. So this typically is a really great object that we look at. Now, it's good to think about binaries because they make up a substantial part of the entire galaxy. And living around a binary system, once you start looking at the numbers, there's definitely, I would say, a probability. You know, if there's life out there, it's probably going to find some in a binary. Well, I don't know if we're going to find some, but there's probably some in a binary system. And I feel like binaries were kind of just like a geek thing until Star Wars came out, and then Tatooine with both suns in the sky, you know, binary.
So Scott, how realistic was the separation of the suns in the sky and Tatooine there? Like, how far apart is a normal binary star system compared to how far the Earth is from the sun?
So there really isn't a benchmark or a base measurement or an average, so to speak. It really comes down to how many, it comes to the mass of the stars, comes down to how many stars are in the system. So you have some star systems where you might have an entire light year between stellar components. And then you have other systems, like especially if you've got like a red dwarf star there, like a really low mass, ultra cool star. You can have stars that are closer to each other than the orbit of Mercury is from the sun. Now, when you think about Proxima Centauri, Proxima Centauri is the closest star to the solar system or to the sun. It's about 4.3 light years distant from us, and this star is an ultra cool dwarf star. It has a small planet around it as well, and that small planet is close. It's considered an Earth-like planet because it's in the habitable zone. It's closer to that star than Mercury is to the sun. So, and a lot of these binary systems we see, you don't always see all the components or all the stars. There's really three different types of true binaries. There's optical binaries where you can actually see the components in a telescope or naked eye, in the case of Alcor and Mizar. There's astrometric binaries, which are binaries where you don't see visibly the components, but you could measure the effects that the components you don't see have on the components that you do see from a gravitational perspective, like a wobble. And then the third type is spectrographic binaries. And spectrographic binaries is where you can take a look at a star, its spectrum, and you take the entire visible spectrum, red, green, and blue, and you break it all out to all the different emissions and absorption lines, and you see what looks like the rainbow. And in that spectrum, you can see the Doppler shift of the really fast, close orbiting binary. And Doppler shift would be as that object moves away around the star, it shifts a little bit to the red. When it moves around the star and comes back to us, it shifts a little bit to the blue. And you can see this shift happening. And that's how we find a lot of these really close binary systems. And even the term binary is somewhat of a misnomer. It's old. It was from a time period when we didn't realize that you could use spectroscopy to find additional stellar components. And we just thought all binary systems were just 2 stars, which now seems to be rather uncommon. But as far as this system goes, Gamma Leo, they are actually 2.
Scott, it seems like we have a couple of questions here. Lindsay, did you want to take one?
Sure. So Charlene wanted to know earlier, she asked galactic collision. Cool. Does one eventually absorb the other? Do they repel or TBD?
So
Or
go ahead.
I can-
Go ahead, Derek.
Yeah. So a lot of times it really forms a new object. The way that the 2 galaxies interact, you end up with kind of all of the stars eventually kind of turning into this like football shape that we sometimes call an elliptical galaxy. And that's kind of like the end game, where the interaction is where you see a lot of interesting things, because you take these galaxies that have, you know, some very well-defined structure, and then you basically disrupt it by running the 2 galaxies into each other. And later on, I was planning on showing another picture where there's a very dense galactic cluster in the constellation Virgo, and a lot of the galaxies there are elliptical. The thought being that they have had so many interactions that they've all kind of evolved into that elliptical galaxy prototype.
A good thing to think about too with galactic mergers is you're not going to have a lot of like stars and planets just crashing into each other. I mean, there's a lot of space in between.
True.
But what you will do is all of that. So if you got, like, say, 2 spirals, like Derek was saying, you know, that structure comes apart. When you have a spiral galaxy, from an aesthetic point of view, the way it looks awesome. But from a star forming point of view, or galactic survival kind of, it's not really all that great, because all of that molecular hydrogen, all those nebula, they're all sitting along those spiral arms in an organized fashion, and it's not mixing together, which is what you need for star formation. When you have these galaxies come together and merge, as Derek was saying, that structure comes apart. And when that happens, all of that, those hydrogen clouds, all those nebulae, they start mixing with each other, and you get a humongous increase in star formation. And for a very short period, that new galaxy is considered a starburst galaxy because of the rate of star formation goes up so high because of all this stuff mixing together.
Sounds cool. We had another question from Minion TM69. How does a planet maintain a stable orbit in a binary system?
As a planet?
It says planet, but I don't know if they meant planet.
So right now, we don't know of too many, binary systems with planets, though it depends again on the mass of the stars that are in the system and the distance of the stars. You could have a binary system where the planets will orbit both stars as a group. But you could also have a binary system where you might have planets that orbit individual stars. You can even have a system where you might have some very close stars that are orbiting and individual stars, and then you have very close, very wide out, very large, more massive planets that might orbit the group. It really depends on the system itself. And it would be a little bit, probably a little trickier for planets to maintain their orbits around these types of systems. But you got to remember, the planets formed with the leftover material from the stars. They've always been there. It's not like they just appeared one day and now have to figure everything out. So they formed in their orbits and they maintain that stable orbit.
And what is the name of this binary system again that we're looking at?
Its designation is Gamma Leo. So it's in the constellation Leo. And its name is Algeba. That's its common name. And when you look at the constellation Leo, you get that it's like a sickle in the sky or a backwards question mark. Algeba will be the second brightest star in the question mark, with Regulus at the bottom being the brightest. So Derek, you want to go?
So having some technical difficulties.
Okay, so let me do this. I'm going to stop sharing the screen real quick, and I'm going to jump over to another image that I have here. Now, actually, Gavin, do you have anything?
Sure, I can jump in with some images.
All right,
here.
you jump on for a bit. We've been trying to get Gavin to set up his telescope outside, and he's just not doing it. So I want everyone this week to write in and be like, Gavin, get it working.
It's not a good season for Gavin's telescope.
Too many experiments were tried.
Well, I mean, that's actually kind of an interesting topic with you. There's a lot of different kinds of telescopes out there, and I have what's called a fast refractor. So it's a very compact light telescope, easy to transport, but it looks at a very wide area of the sky. Actually, let me fast forward my images here. This is Messier 42, the Great Nebula in Orion. And it's probably about as far across as the full moon. And it basically fills the view of my telescope with my camera attached to it. But now in the springtime going into the early summer here, it's called galaxy season. And a lot of these galaxies that are up, they're very spectacular to look at. They're very much smaller in an angular sense. Obviously a galaxy is much larger than your Orion Nebula, but from Earth they look much smaller. And that's where you need a telescope with what they call a longer focal length. So it's providing more magnification. That's the instruments that Scott and Derek are using this evening are called Ritchie-Creighton reflecting telescopes. They compact things down with mirrors and give you a more zoomed in view.
Don't listen to Gavin's excuses.
All right, I think I'm ready. So, if you're good, you can continue. All right. So I have a picture of M67, which is an open cluster in the constellation of Cancer, and this is always a slow process for me. Yeah. So this is probably one of the smaller of the open clusters. I was trying to show you the Beehive cluster earlier, and I realized that I'm looking at like a third of it with my telescope instead of the whole thing. So I had to go find a smaller open cluster. So this is M67, and it is one of the older open clusters that we've discovered in the Milky Way. And the difference between the globular cluster and an open cluster is that a globular cluster is, it's a much more gravitationally bound grouping of stars that is mostly spherical, and it has a different origin. They're much older objects, and what an open cluster is kind of the remnants of a star forming region. After stars have formed and started to blow, basically push the gas out of the area that was used for star formation, the open cluster is what's left behind, and then they have some gravitational interactions that either spread out the group or other things can happen there where you might end up with stars capturing and making binaries and getting ejected together to make a binary system or a trinary system, as it were. This one is in kind of the southern part of the constellation of Cancer. And then that, if you don't know where that is kind of, if you're looking at Leo, it's to the east and a little bit to the south of Leo in the sky. So, I don't know if anybody else has anything to add about M67 or open clusters, but that's kind of my spiel on open clusters.
With clusters, Derek, are there, I was going to say, how many different types of clusters are there? Are there just the two of open clusters and globular clusters?
For the most part, those are the two that I know about. I mean, in the depths of the astronomy field, I wouldn't be surprised if there's some classification that is, a third or fourth there, but I don't know them. Maybe Scott can provide insight.
Gotcha.
I was going to add, Derek, the distinction between a globular cluster and a open cluster isn't just from their appearance. There's also a difference in the way they form, correct?
Correct. Yeah, I actually don't know how a globular cluster forms. When I was giving that, that kind of monologue, I was like thinking about it. And I've read about how open clusters form, but I've I don't think I've ever read about how a globular cluster formed.
How about an open cluster?
Yeah, so to elaborate, an open cluster, so the picture I was showing of the Great Nebula in Orion there, it's this star-forming nebula with a lot of gas there that was hot and glowing, and that's what produces the nebula. Later in its life, as that gas is consumed, it's going to transition into an open cluster where those stars that it formed are still there, but that gas cloud has dispersed or been used up.
All right, let me see if we can find something else to look at. Well, we'll leave that up while some questions might come in about it.
Does anyone know how many clusters there are out there that you can view?
There's a lot. Off the top of my head, I can think of a couple dozen between globular clusters and open clusters. M44, which is the Beehive cluster, is at the other end of Cancer. So this is an area of the sky that has at least 2 well-known open clusters. And then if you go, the Pleiades is another well-known open cluster. That one is much closer to Earth, so we actually can see the component stars naked eye. And let's see, is there another one off the top of my head I can think of? I don't think so. But from a globular cluster standpoint, we showed a couple weeks ago. M13 is probably the largest one in the northern hemisphere that we talk about. That's in the constellation of Hercules. And then we showed M3 and M53, I believe, a couple weeks ago.
Yeah, I would say like in the Messier catalog, which is a useful catalog of things that are fairly easy to view as an amateur astronomer, I'd say at least a third to a half of it is probably clusters of some sort.
Yeah.
Maybe you guys know, what's the history with Messier? Like, was he an astronomer? Was he a scientist? Was he?
I gave that spiel last time, so I'll let somebody else do it.
Okay.
So Messier was interested in studying comets because they're really cool to look at, as we've seen with the comet Swan coming by. But when you're looking out there and you've got this fuzzy spot in the sky, to classify between a comet or the number of other kinds of object out there, you kind of track its movement. And once you spend a lot of time doing that, if it turns out that it's not a comet, that's kind of annoying, and you want to mark down where you saw that so that if you come back to it later, you know not to go through all that trouble. So Messier was actually putting together a catalog of fuzzy things in the sky that he could see with his telescope that did not in the end turn out to be comets. And that actually turned out to be very useful for us amateur astronomers because we have equipment similar in capability to what Messier had. And these are all things in predictable positions that have other cool properties, like being open clusters or galaxies or nebula.
Oscar had a question here. He said, how many stars need to be in a cluster for it to be called a cluster? Is there a minimum?
Generally, Oscar,
go ahead, Scott.
What usually happens with that is when you start getting, it's not so much about how many stars are there. It's more about what's the history of the object. So is this a product of star formation? You know, when you got a molecular hydrogen cloud, a nebula, and star formation starts happening there, you'll end up forming a couple of thousand stars. And eventually those stars will blow away all that hydrogen gas. And what emerges is an open star cluster of stars. So the open star cluster will eventually break up into individual star systems, though while it's in that cluster stage, we call it a cluster. Now, you also have groupings of hundreds of thousands of stars like globular clusters, and they all share at that, again, a combined gravitational equilibrium that holds them all together. If you have 3 or 4 stars in a system together, we don't call that a cluster because this is something that is a product that came out of a cluster. We would call this a multiple star system. I'd say pretty much when you start getting into hundreds of stars, you're talking clusters. When you're talking 10 stars, you're talking multiple star system.
And I think the Pleiades is probably on the low end. It has, I don't even think it's technically got 100 stars in it. I think usually what I read is it's in the high 40, 50s. But I might be crazy.
Let's see here.
Sorry, watching my telescope so it doesn't crash into itself. as it moves. It tried to do that to me the other night. That's not going to do anything for us. Yeah, this is really surprising that it's clear out. Yay, New England.
Yeah, looking at the weather
right?
report this evening, it was supposed to get cloudy around 8 and then get progressively worse. So
Yeah. So they get for the power going out last night. I was running around trying to get all the things fixed up this morning. All right. Let's see if we can line up on this. I think I'm going to try to find a double star and see if I can find a different one from what Scott showed you earlier. I unfortunately can't do video. That might be my my goal for next week if this continues.
So let's see here real quick. Let's throw up an image real fast of Markarian's chain. Unless you got something live there.
Yeah. No, not yet. I'm still. It takes a lot longer than I would think to jump between objects. It's really kind of fun.
Right. Here. Let's do this. Needle.
So what Derek's having to do here is, even though we have computer control of our telescope, that it knows where the stars are and can move automatically between them, is he needs to give it reference points to know where it's starting from. So he needs to manually find things that he can easily recognize, and then the telescope can move down to fainter and fainter objects that from the catalog.
All right, so this is an image of an object called Markarian's chain. And what you're looking at here is a series of galaxies that are all connected to each other, and they're all part of what we call the Virgo cluster. Now, this is an image that was captured by our speaker last week, Bob Horton, up at Brown University, and we were working together on the image, and I'm the one that processed out the image data that he submit. Now, in this image, you're looking at a section of sky that's roughly about just under 1 degree of width that all of these galaxies are in. If you have a telescope with a wide enough field of view, you can actually see all these galaxies together. Now, when you're looking at this image, you'll notice that there's a lot of elliptical galaxies in it. This is a good example of an elliptical galaxy, which is what Derek was talking about earlier, where you don't have the spiral arms. You don't have that dust lane or those dark regions. You don't have a bar coming off the center. It just looks like a bulge in space that gets brighter towards the middle. And these elliptical galaxies are largely comprised of very old stars. And there's not a lot of star formation going on in them. They're all very old stars. They're old galaxies. Galaxies like this guy here and right over here, these are on-edge spiral galaxies, which means that, if you take a galaxy, think about a spiral galaxy. If you look at it from the top down or the bottom up, you see the bright nucleus, you see the bars that come off the nucleus, and then the spirals that come off the bars. But if you flip it on its side and take a look at it, it just looks like a thin line with a little bulge in the middle. And that's the galactic plane you're looking at. These galaxies right in here, we are looking at their galactic planes because they're tilted almost on edge. Now, they're not completely on edge, especially this guy right here. This chick is slightly tilted a bit so we can see it just across that plane. But when you come down here a little bit, you got these two galaxies. And one of these galaxies is just a mess. That warp that you see, that's called perturbations. And that's a disturbance due to the gravity of another object. These galaxies are coming together. They are merging, like we were talking about earlier. And that merger has disrupted the entire galactic plane and sent all those objects into disarray. So it's a good chance that these galaxies already had one swing right through each other, and now they're kind of spinning back out to come back in and do it again. And when it did that, it blasted out all of those stars and all of that galactic matter into the area around the galaxy. That's what galactic mergers look like. Now, if you come down the chain a little further, you start seeing that there are some face-on spiral galaxies, as well as a few other little elliptical galaxies and other face-on spiral over here. And in the background here, it's important to note that though you do see stars out here, that's a galaxy, that's a galaxy, that's a galaxy, that's a galaxy, that's a galaxy. I mean, there's galaxies all over the place here. These are galaxies back here. A lot of these, what at first glance look like stars, are galaxies. And the Virgo cluster is part of what we call the Virgo supercluster, which is a huge cluster of galactic clusters and groups that the solar system is part of and the Milky Way galaxy is part of. We're in a group called the local group, and the local group is part of the Virgo supercluster. Now, we're not in the center of it. You know, we used to think we were in the center of everything, but we realized that we're not really that important. But when we look at the galaxy, this cluster, we see this. We see just thousands of galaxies. And this is very similar when you think about to like the Hubble Deep Fields or the Hubble Ultra Deep Field. Now, we used to think that this was just the only galaxy. And then when we started figuring out that Andromeda and Triangulum, which are galaxies in a local group, were also galaxies, we figured, well, maybe there's a few galaxies out there, you know, us and a couple other. And then we just kept finding more and more galaxies. So we decided to do the Hubble Deep Field. Take Hubble, point it to a spot in the sky that's right off the end of the handle of the Big Dipper, and let's just expose it for like 30 days and see what we see. And when we process those images out, there were thousands of galaxies in the image, just galaxies everywhere. So they choose a little section of the image, like a pinky nail section of that image, and then they did the same thing. And in that image, the same thing, just thousands and thousands of galaxies. And that brings us to today, where we now understand that it's not 2 or 3 galaxies out there. There are trillions of galaxies out there. And looking at Markarian's chain is a good reminder of that. You got that binary, Derek?
I'm actually going to line up on a globular.
Oh,
but
nice.
Yeah, I have to play with a lot of settings to make this work, so it's a little slow.
Gavin, you got something?
Sure, I can hop in here with another picture.
Just going to add in about that picture, Scott, that you have up with those galaxies. When you first put it up, it would have been fun to kind of put out there. How many galaxies can you find?
Yeah, right. One of the guys I work with up at Brown had submit just so I could check out a picture from one of the projects they're working on, and it's of a Bell cluster. It's called a Bell 1605 in Virgo, and like when they sent me this picture, there's so many galaxies in it that I sat there for like 2 hours just looking around it, and I wrote them. I'm like, wow, thanks for that. I just lost 2 hours of my day to this image, but it's just astounding. Gavin, that is an awesome image you have there.
Yeah, so what we've got here is the Horsehead Nebula. This is also in Orion. The very bright star just to the left of image center is actually the leftmost star in Orion's belt. So there's a cloud of hydrogen gas here. You kind of see there's a ribbon moving off to the right. And then in front of that, there's actually a dark cloud of dust matter that's absorbing some of that light that forms the horse's head in the center of the image. So there's a lot going on here in terms of objects layering with each other. The other object in this frame is down to the below the bright star. There is the Flame Nebula, which is associated with the same molecular cloud, but it's kind of a distinct object. Again, with some of that dark banding through from the intervening dust clouds.
All right.
With these nebulas and the naming of them, like who actually discovered them, or how long have we known about them?
That is an excellent question.
Well, if you think about, so the Orion Nebula, for example, I mean, this is a naked eye visible object. So we've been able to see that for an extremely long period of time. But a lot of these objects were discovered by like early astronomers, especially with their bright objects. But Charles Messier discovered a lot too. And if he didn't discover them, he at least cataloged them, because the other astronomers weren't cataloging when they found them. And that really got him upset when he was looking for all his comets. So when he created that catalog, though, along that way of looking for comets, Charles Messier did discover a lot of these brighter nebulae and galaxies that are out there.
That's another great picture there.
So to kind of put
yeah,
these objects in perspective, I took a broader field here. This is the constellation of Orion. You can see the belt through here and the brighter corner stars. So the object that we were just looking at, the Great Nebula in Orion, is right here at the bottom of the sword. And the Horsehead Nebula is here along the belt. So you can kind of get a picture of like how much sky this is taking up. So these are both, particularly the Great Nebula there is a great object to see through even binoculars when you're getting started with astronomy.
Yeah, that is a great area of the sky to do binocular observations, especially in the winter, because we don't have a lot of good Milky Way arms to look through in the wintertime like we do in the summer.
The other object you can see in this frame is from a macroscopic view. You can see this arc of gas here. It's Barnard's Loop, which is kind of a shock wave in this huge star-forming region here.
And the brightness on the right side of the image, is that sky glow, or is that something else?
That is terrestrial. That is the city of Westerly. When I captured this image, Orion was just starting to set into Westerly over Frosty Drew. So when we capture these images, that's one of the things you kind of have to plan for is not only the sky needs to be clear and it needs to be the right time of year, but even over the course of the night, the object's going to pass across the sky, and at what time is it going to be in the darkest spot? For Frosty Drew, it's to the south and the southeast. For my own home here, I kind of try and get things closer to the west. It all kind of depends. The actual attributes of your viewing location kind of play into this.
All right, so I've got a globular. We want to show that to basically give us a distinguishing, or to be able to show what the difference is between a globular and an open cluster. So this is the object M53, fresh from the telescope. It's a little bit interesting to get these images and try to do this as a live session because cameras are much different than the human eye from the way they collect light. You can see the stars are, very much blown out, saturated, and we really don't start to see the faint object but its core is blown out. And if you look at this naked eye, these stars would be, crisp points of light, and you would really see this really nice pattern of stars that just kind of emanate from the core of this cluster. In this particular cluster is, there's tens of thousands to probably upwards of 50,000 stars all tightly grouped together there. Whereas an open cluster, as we said, on the order of 100 stars. So there's a massive difference in the number of stars that make up these objects and also where they are in the galaxy. Globular clusters orbit the Milky Way. They aren't really within the Milky Way. They are gravitationally bound to the Milky Way, but they are not what you would say along the galactic disk. Open clusters generally are. They are, part of the star-forming regions of the Milky Way, and they are fairly young objects when compared to globular clusters, which can be as old as the galaxy itself, 10 plus billion years old. And in this one, I'll zoom in. You can kind of get an idea for how dense the stars get. It's a little grainy because it's a quick image at high gain, but you can really see like how densely these stars are packed together to the point where like the light just merges in the middle there.
Yeah, that's really cool.
So
We had a question here from Mr. WM. I think he was referring to Gavin, one of your pictures. He said, great pick. Meant to ask about earlier picture of Virgo cluster. Curious if a tracking 10-inch reflector and typical DSLR would be adequate to get a similar capture. Thank you.
So the picture that Scott showed of the Markarian chain, that's actually a really wide field. That's probably 5 or 6, maybe even 8 moon. If you did it in width of the moon, moons across. I don't know that you would get the wide field if you used that type of instrument. That was probably shot with something in the, I'm going to guess, 300 millimeter class of optical instrument.
Yeah, it's the 8-inch astrograph f4.
Okay, so that's 800 millimeters. Oh, so it's a little tighter than I thought. So one of the other things I had was actually a close-in shot of one of the pairs of galaxies in the Markarian chain called the Eyes. I didn't get a lot of time on this, so there's a few artifacts here. But this is M86, which was that giant elliptical galaxy that you saw in the picture that Scott had. This is one of those edge-on spiral galaxies, and then this is that pair of galaxies that was interacting, where this one has that highly distorted gas diffusion around it.
Go back to the edge-on galaxy and magnify that again. That's great. You can see the dust lane in there. So you see that dark band that's in that galaxy. What you're looking at, that's all interstellar material. That we call it a dust lane.
The other one is cool.
Yeah, look at that too. That's great. You got some really excellent. Well, that one is just highly perturbed.
Oh yeah.
So,
and
you're talking filament, cold hydrogen gas.
Yeah. This filament here there's some research that suggests it's actually gas in between the Milky Way and this galaxy and not necessarily part of this galaxy.
Okay.
I was reading about this as I was processing the images because it takes a while for the computer to do its thing sometimes. You just go calmly read about the object that I'm processing. You can kind of see how different the dust lanes are in the core here and how different these, gas or dark dust lanes kind of exist. And then, you can kind of see the shape of this one's already starting to get, kind of turned into that elliptical galaxy when you compare it to something like this, which is that edge-on spiral, or at least a barred spiral. And then, just this.
Now, how long of an exposure is that, Derek?
This is a stack of 31 2-minute images. This is a piece of dust on my camera, so please ignore that.
That's how you know that Derek didn't shoot his flats or his darks.
That's new dust. So this is not in my archive. But you can really see, here's a galaxy, here's a galaxy, here's a galaxy. Just background galaxies. They're everywhere. There's one. There's one.
Oh yeah, that's great.
They're just. There's another one right here. You can barely see it, but it's there. There. Sorry, I'm jumping around the image, which is probably driving people viewing this nuts. But it's just crazy how many galaxies are out there, and this is just. In this telescope, field of view is about the width of the full moon. Like if I took a picture of the moon, it would fill this frame left to right. Just to give you an idea of what that spatial size is for the sky.
So I have an image real quick here. So this here, this is more of we're starting to see this now later in the night, but this is part of a region of the sky called the Summer Triangle. And this object is called 61 Cygni. Now, 61 Cygni, this is a binary star. This is a fantastic example of a binary star. 61 Cygni is very close to us as well. It's about 11.4 light years away from us. Now, both stars in 61 Cygni are very similar to each other. And they're called K-type stars, which is on the cooler, lower mass side of the spectrum of stars that we see in the sky. The sun is a G-type star, so it's one category hotter and more massive than these two. Now, these stars have a stable gravitational balance with each other. They orbit around each other. And this is not necessarily naked eye visible, this star. You need a telescope to see it. This star also has a very interesting property about itself. And when you think about stars in a galaxy, stars move along the galaxy, but they move at a rate that's so slow that we don't notice changes by looking up at the sky. But you can measure them, and this is called proper motion. 61 Cygni's proper motion is significantly faster than other stars in the galaxy. And you can see visible changes in 61 Cygni's position over a period of 10 years. So this is something we frequently observe as we get into the summer months and then the autumn months at Frosty Drew, because it really looks amazing in the telescope. And this is yet again another example of a binary system. Now, I was talking real quick about the summer triangle. And we have put up an image real quick right here of the summer triangle. So the summer triangle this is an asterism. And you'll notice on the screen here you have 3 bright stars that form a triangle. And an asterism, we talked about this a little bit last week, an asterism is a familiar shape that we see in the night sky, but it's not an official or one of the official 88 constellations. So things like some common asterisms you guys probably heard of, aside from the summer triangle, the Big Dipper, the Little Dipper. These aren't the constellations, these are the asterisms. The Big Dipper's constellation is Ursa Major, and it's actually the Big Bear. The Sagittarius, the constellation is the Archer, but what we see in modern times is the Teapot. So the triangle is not a constellation. It's actually comprised of 5 constellations. Up here, you have the bright star Vega. And Vega is part of the constellation Lyra, which is visible as this little parallelogram right here. The second brightest star you're going to see in the summer triangle is the star Altair. Now, Altair is also pretty close to us. It's about 16 light years distant. And this is part of the constellation Aquila the Eagle. Now, the eagle is not fully visible in this image because it kind of runs off to the bottom here. But if you're out one night at Frosty Drew, when we can actually accept visitors again, ask us to point it out to you, and we will. And then you got the third brightest star in the triangle. This is called Deneb. And Deneb is a very interesting star because, you know, Vega is about 26 light years away. Altair over here is about 16 light years away. But Deneb is about 2,000 light years distant. I mean, it is out there. It is a massive blue giant, we call it. And it sits right along the galactic plane. So when you're looking at this image, you can see all of this dust and all this reds and these blacks here. And what you're looking at is the Milky Way. This is the Milky Way galactic plane, which cuts right through the summer triangle. And you got a lot of really great things in this image that you can spot. I mean, you have this here is another asterism. It's called the Northern Cross is what we call it, or the Cygnus Cross. I will zoom in on that region for you right now because there's a lot you can see there. And this is one of the reasons why I like the summer sky so much, because there's just so much going on there. So this here is the Northern Cross. You have Deneb at the top. In the center, you have the star Satyr. This star over here is Gyna, and this star is Rook. And down here, you have Alberio, one of the most famous binaries in the summer sky, or in the sky altogether. And right over here, you have what we call the Satyr Cloud Complex. So you have a lot of hydrogen gas in this region, and it's near a lot of stars. You're talking galactic plane. And the stars that are near this hydrogen gas, they're casting their intense ultraviolet light into that gas cloud, and they're ionizing those hydrogen atoms. That ionization process, and you blast off an electron, and now you got an ion floating around. And those electrons, they want to reconnect. So when they come back together, they get excited. And when they return to a ground state or a restful state, they release a little bit of energy in the form of a photon, and we can see that. And they glow. And that's where all these reds you're seeing are coming from. Now, you also have this object right over here. And this is a cluster of stars. It's actually called the Vulpecula cluster. But then down here, now this is probably one of my favorite objects in this region of the sky. You notice you got this wisp right here, and then you got this curve right down here. This is called the Veil Nebula. And this is a supernova remnant. And this is the remnant of a supernova that occurred in that area of the sky. And that supernova occurred quite a while ago. I mean, it's not like, it wasn't yesterday. So this supernova the star was probably about 20 solar masses when it exploded. I mean, when it's supernova, it happened about 21,000 years ago. I mean, we're talking a long time ago. The current distance of this object, of this supernova remnant, it's about 2,500 light years from us, and its radius or its diameter is about 130 light years. So this thing is pretty big. And though the veil is largely this piece here and then some of this up here, this whole area is called the Cygnus Loop. This is another object that we frequently look at Frosty Drew during the summer months. It really is quite fabulous. Derek, you have anything to add about the image, or Gavin?
I actually wanted to show Albireo right in the middle, or actually in this image, it's towards the end of, the upper right. You've got this super bright star that is a double, and that is probably one of the more popular doubles that we show visitors at Frosty Drew. And if I could share my picture of that double, I think everybody would enjoy that for a few seconds, and then I'm going to have to close the roof because we've got clouds here.
Yeah, I'm clouded out as well.
All right. So this was taken a little while ago, but luckily stars don't change very much. So this is the double Albireo, which is the head of the swan of Cygnus. And we show this at Frosty Drew quite commonly because it is probably one of the most contrasting doubles that we know of in the night sky.
That's a fabulous image, Derek.
Thanks.
I love the diffraction spikes.
Really well. Yeah, I like them. I like to keep them. Some people try to get rid of them.
I keep them.
I think if I did this image again, I'd turn the telescope a little bit so I could actually align the deflection spikes so that they didn't cross over the star, the blue star. But anyway,
I was actually going to ask if you had rolled your tube just to get them on a line like that.
I don't think I did. But what's really cool about this star, and this picture does a pretty good justice to it, is the amount of color difference there is between these two stars. A lot of times when you look at stars in the night sky, it's like, oh, that's a little bit orange, that's a little bit white. But you look at these two, and they're so close together. They're in the same frame and you can really see, oh, that one's orange and that one's blue. And some people actually see it as orange and green, or white and green, or white and blue. And that really comes down to just the composition of your eye and the rods and cones as to what colors you're more sensitive to. So it's a really fun discussion to have with the people at Frosty Drew. And unfortunately, the camera has this answer, and everybody gets to look at the camera's answer, so we can't have that discussion when we do these live streams on YouTube.
Another thing too, when you see these colors in stars, what you're looking at is the temperature of these stars. Red stars are the cool stars, and blue stars are the hot stars. And when you can visually see these temperatures, it gives you a little bit of idea about the mass of these stars as well. So even though in this image that blue star looks smaller than the orange star, the blue star is higher mass because it needs a substantially higher amount of mass to be able to get the temperatures up that high. It's not always about size. Think about mass as weight. Like a good way to think about this is a bowling ball versus a beach ball.
And this is, I believe, an optical double. Is that correct, Scott?
It is. So yeah. So that's kind of been a matter of debate for some time now. What is alberio? Is it a true binary? Is it an optical binary? Now, an optical binary is where you have two stars that, though they appear to be together from our point of view, they're actually not. It's just a line of sight issue that we see. And we can detect this. So a true binary needs to have pretty much one of three measurements. Either one, we can see that orbital motion. Two, we measure their distance. And if their distances are pretty much the same, then we know they're together. And three, we can take a look at their proper motion and see if their proper motions match. If the proper motions match, then they're together. With alberio, all of these factors for a while now have kind of sat on the fence. We measure their distance, and they're pretty close. Anywhere from, but they're not close enough to necessarily be together, 10 to 15 light years apart. But it's not impossible. It's just very unlikely. So we take a look for orbital motion, but if the 10 to 15 light years apart, you're not going to see orbital motion. We'd be talking 100,000 year orbital period. So we look at proper motion, and for a while it looked like they might be sharing a common proper motion. But now that we have better devices in space looking at these stars, and in this case, the European Space Agency has a mission called Gaia that's performing parallax measurements, which is a distance measurement on over 1 billion stars, and alberio's on a list. Gaia has identified different proper motions between both stars and has potentially identified a very close companion star to the orange star in this picture, which is called alberio A. So
cool.
That's not the nail in the coffin, but at this point we're leaning towards, yes, an optical binary.
Pretty cool. The fun thing about doing this stuff is there's always new information coming in from the skies above.
Yeah, and there's a good point with that too, is that this really is, we're on the bleeding edge with a lot of this stuff. And as a scientist, you have to ask yourself every day, what don't I know and what do I want to know? Because if you can't say I don't know, then you're not functioning very well as a scientist, because that's what drives science. And when you think about what we do know about the cosmos and the galaxy and the universe, it sounds like a lot, but it's actually not. There are gaps that are so big that there are processes that we know function, that we know are true, but they kind of counteract each other, which means that there's so much of it that's happening that we don't know, that the things we do know don't always work well together. And I also hear a lot of visitors and just a lot of people in my daily life will bring up, how come it's always changing? How come we're always wrong? And it's not that we're wrong. It's not that we're disproving things that we used to think were true or facts. It's that science is always getting better. So we're improving what we know. We're building on top of what we've already learned. So don't think about it as us getting it wrong and then getting it right later. It's us getting better. And when you hear about not finding something, so say you're looking for dark matter and the project that you do turns up absolutely nothing. That is just as good from a scientific perspective as finding something. Because now we know that using those techniques and those methods are no longer adequate or suitable for finding what we're looking for. And we also know that that piece of material or the subject of that research does not function in that area. So just because you found nothing doesn't mean that you failed. It means that you've completed what you were going after.
It's all about refining, iteratively refining. Wow, it's Friday.
I hear that.
it's a good point too that a lot of when we show these objects, we're reciting names of things that have been memorized. We're talking about 150-year-old star catalogs and things. I mean, that's a basis of things that are interesting to look at. But there are these unknown questions. There's a lot of science still to be done, and like when you enter the field of astronomy, it's not like taking a history lesson. It's learning techniques and how to come up with new techniques to test new theories and that sort of thing.
A good thing to think about too is that, like Gavin's saying here, another reason why we keep getting better with it is because physics discoveries drives new technologies, and those new technologies enable us to make better physics discoveries and get a better understanding of physics, which then give us the ability to create better technologies. It's cyclical. It compounds on top of itself. It's logarithmic. So I got an image right here of Sagittarius that I'll throw up real quick. So now Sagittarius is where the Milky Way's galactic nucleus resides. And this is a very popular part of the sky for us at Frosty Drew during the summer, because from our location, the Milky Way is extremely visible. I mean, it's not where I am here in Providence and where Gavin and Derek are. You're not going to get the Milky Way there. But at Frosty Drew, you do. And in this view here, we're looking at this over here is the galactic nucleus. This whole bulge is it. But the center of the galaxy is roughly right in this area, right over here. And in the center of the galaxy is an object called Sagittarius A star. And that is a supermassive black hole that the galaxy is just centered on. Now, we can't see it. Black hole, we're not going to see it. But we couldn't see it anyway visibly, even if we were able to see it, because there's a lot of other things in the way. But we can look at some of the stars around it and how those stars are orbiting in a very strange way around that black hole. Now, in this image here, we have a lot going on. You'll notice this dark dustiness that you see everywhere here, this wispiness. And this is another arm of the Milky Way galaxy that sits in between where we are, the solar system, and the galactic nucleus. It's called the Scutum Centaurus arm, and it blocks a lot of our view. But along that arm, we see a lot of really great objects. Like this here. This is called the Lagoon Nebula. And this is a site of star formation. It's about 5,000 light years distant. It's about 25 light years in diameter. And it's one of two naked eye visible star forming nebulae in the northern hemisphere. Right next door to it, right here, you have the Trifid Nebula. The Trifid Nebula is also a star forming nebula. I mean, you got a lot going on in this region of the sky. All of the yellows you see in here, these are all stars, all older stars that are residing towards the center of the galaxy. And then right over here, you have the constellation Sagittarius. And Sagittarius looks like a teapot. And I'm going to do something now that's kind of a fallacy. It's kind of a scientific fallacy. If you don't see it just by looking at it, then someone shouldn't have to point it out to you. But I'm going to point it out to you anyway. So you can chide me on that if you like. This is what we see as the teapot in Sagittarius. And this is another really common asterism that we see today. And if you think about it, asterisms, though they're not official constellations now, down the road, they may become constellations one day. I mean, that's all constellations are, just familiar shapes we see in the sky. And the Star Lore catalog that we subscribe to, largely the Greek catalog, comes down to a lot of Zeus's, fornications and some of his infidelities or other people who hurt people. I mean, not a lot of good stories in the sky right now, but maybe one day there will be. But this is a fabulous area of space that we see down at Frosty Drew. Another thing to take a look at in this image as well. I mean, I'm not going to spend all night on it, but right here, this what looks like a star here. This is actually a globular cluster. This cluster is called Messier 22, and it is first of all, it's an elliptical globular cluster, which there's not many of them. And this globular cluster sits along the galactic plane, which is also kind of weird. And it's quite close to us. Most globular clusters are roughly 33,000 light years distant, because they all reside in the halo. I believe Derek was talking about this before, where Messier 22 is only about 16,000 light years distant. And that puts it into a classification of globulars that may actually be the remnants of galaxies that we've already absorbed, where the central region stayed intact.
So that goes into that where I said there's probably more than two. That's probably the more than two classifications of clusters.
Right.
So this is the weird one, and the weird ones are the ones that start new categories.
And it's those weird objects that they drive us. It's like we want to figure that out. We want to know what is going on there. Now, this time of the year as well, we have another great constellation in the sky that most people don't know of, and it's called Coma Berenices. And this here is an image of the constellation Coma Berenices. Now, Coma Berenices, it means Berenices is hair. I don't know the background of the story of this constellation. I'm not really great with all of that stuff, the star lore. But what you can see, even if you look up at the sky over a relatively, like, it doesn't have to be dark like Frosty Drew, but you don't want to be doing it in, say, Times Square. You'd notice that there is this little chunk in the sky of stars that seem to be all kind of congregated in a little triangle. And it's right behind the constellation Leo. And that's Coma Berenices. And this is pretty much what you see, is this cluster of stars. And this is one of the indicators of the Virgo supercluster. So when you think about space, so you got Leo, you got Virgo, and you got Coma Berenices all within the same general area of the sky. If you know enough about the constellations, or you're down at Frosty Drew so we could point it out to you, the tail star in Leo, or the lion's tail, is called the nebula. And then Virgo, it's supposed to be the Virgin, but it looks more like just a Y in the sky, like the letter Y. The top left star in the Y is called Vendemiatrix. And if you make a triangle, make a line between Vendemiatrix and Denebula, and then make another line from Denebula to Coma Berenices and back to Vendemiatrix, that triangle in the center of it is the center of the Virgo supercluster. And that's where Mercurian's chain is. That's where M87 is, that big crazy galaxy that we got the picture of the black hole from. And that's where you see just this galaxies that are everywhere, that are easy to see. I mean, there's technically galaxies everywhere, but they're not as easy to see as they are in this region. So I threw this image up last week, and I'm going to do it again tonight because you guys need to get excited. This is an image captured by a fantastic astrophotographer, probably one of the best in the world. His name is Damien Peach. Now, we didn't capture this image. Damien Peach captured this from a telescope down in Chile. And this is comet F8 Swan. This is the comet that's all the rage right now. I mean, look at that comet. This comet has formed such an amazing tail behind it. We haven't seen a comet do this since probably Comet Q2 Lovejoy, which was back in, what was that, 2014, 2016?
13, I think.
2013?
Yeah, I think it's been that long. I was looking through some of my pictures the other night, and I think it was designation was like 2012 Lovejoy, something C2 Lovejoy, and I was imaging it in 2013. So,
I mean, that was just such a fantastic comet, and this comet reminds me of it. Now, Comet Swan is a new comet. It's so new that we don't know too much about it. Like, we haven't calculated, or last I checked, we hadn't calculated its orbital period. Is it a long period comet? Is it a short period comet? Meaning, does it have a longer than 200-year orbit or less? And the comet does have quite an inclination to it. So when you think about, we were talking about galaxies before, top down, the galactic plane. The solar system has the same thing going on. If you look at the solar system from the top down, you got the sun in the middle, you got the planets everywhere. But if you look at it from the side, you pretty much have the sun in the middle, and then you have like a line of planets. And you're looking at the galactic plane. Comet Swan is inclined about 43 degrees, I believe, to the plane of the solar system. And it's coming up from underneath us, so to speak, or the south side of the planet. which is why you're getting such great views in the southern hemisphere. So last week it crossed the plane of the solar system. We call this the ecliptic. And that puts it into the northern hemisphere sky. But we have to wait till the moon departs because the moon is in the sky with Comet Swan right now. It's the morning sky. But we're placing the date roughly May 19th when we're going to start seeing Comet Swan. And let me remind you, Comet Swan is naked eye visible. And it could get a lot brighter as it reaches perihelion, its closest point to the sun. Now, there's a lot of things to look at in this image. So this green area you see around the comet's nucleus, this is called a coma. And this is an atmosphere that forms around the comet's nucleus. And it's a product of all the outgassing that's happening on the comet when it encounters the solar wind. I mean, the solar wind is just a constant output of energy, magnetism, plasma from the sun. And it not only does it protect us and creates the heliosphere, like this bubble that surrounds the solar system, but it also interacts with just about everything in the solar system. And as comets move in towards the sun, they get closer to it, they start encountering a heavier solar wind, they start to outgas. That outgassing also leaves behind a fantastic trail of material behind the comet, and it also causes little pieces, little atoms inside that outgassing, that material to become ionized. And those ions will reconnect and they glow a little bit, and that's where we get the ion tail. Now, looking at this image though, you have, so this little bump you see here, this little bump you see over here, right in here, these are called tail disconnect events. You have another one down here, over here, and right here. Tail disconnects are products of things that are happening on the sun. So things like coronal mass ejections or interplanetary shock waves or coronal holes, all of these things affect the solar wind, and sometimes they'll blow the tail right off the comet, and then a new tail forms right behind it, and that's called a tail disconnect. When you get these fabulous tails behind comets, you can start cataloging disconnects. And there's been, when we were looking at Comet Q2 Lovejoy that we were just talking about before, we were able to see tail disconnects in real time when we were imaging the comet. They were happening so frequently. Now that was definitely closer to solar maximum, which we're not at right now. We're at solar minimum right now. But we are still seeing tail disconnects with this comet. But get excited about this. Once we start imaging the comet, we're going to start posting finder charts to our Facebook. It's just facebook.com/Frosty Drew Observatory, and that'll give you an idea where to look for the comet.
So Scott, you mentioned that the features in the tail there kind of tell you like the history of the solar wind interacting with the comet. About how much time does it take for material to get from the comet into the end of the tail that we're seeing in the picture here?
So this happens quite quickly. You're talking about a period of maybe half a day. You would see that material streak out like that, but the tail is also going to move with the comet. It's not stationary. So it's not like the comet's blasting past and the tail just stays there. It does move with the comet. Now, I'm going to relinquish my screen real quick, guys, because it's starting to rain here, and I got to get out of the rain. So, and I'm going to turn it over to Gavin and Derek for a little bit so I can get out of the rain.
All right. I'm going to see if this works. Because Scott was talking about where we could see the Swan comet. I actually brought up the Sky Live Planetarium, which is a web-based planetarium software. Let's see if this sharing works, and we can talk about where that is in the sky. Yeah, let's see if this works. All right, so you have to let me know if you can see that.
Yep, I can see it.
All right, perfect. So this is the comet here. As Scott said, it is visible above the horizon in the northern hemisphere. Let me make sure my location is set here. We're in, apparently, yeah, I mean, it's close enough. I mean, it says United Kingdom. That just means it's going to be off by a few hours about how far above the horizon this is. But the important part I wanted to talk about was where in the sky it is. So you've got the constellation of Andromeda here.
What's that?
We've showed you pictures before of the Andromeda galaxies.
So
I think Gavin has shown you a picture of Triangulum.
The eyepiece hole on the back of the telescope, and then turn the lock screw.
All right, can we mute Scott?
No, on the back of the telescope. Right.
Yay, perfect, thank you. So some things constellation-wise, we've talked about at Frosty Drew, is you've got the Andromeda Galaxy and the constellation of Andromeda, and that basically lines up with the Great Square of Pegasus, and that's usually how we find that. So you've got these 4 guide stars there, and then the Andromeda stars go off this way, and then if the same distance you would go up to find the Andromeda Galaxy, kind of go down to find Triangulum, and then you've got the Triangulum constellation, and that's where the Swan Comet is. And if it is naked eye visible, it's definitely visible with binoculars, and those are usually a very useful tool for going comet spotting. So if you're up early in the morning, might be worth a try. All right. So I know I have gone down to like the southern coast of Connecticut over Long Island Sound to be able to see these sometimes, because they're usually very low on the horizon. It always seems like the southern hemisphere gets the better deal with comets. They always seem to come from the south, go up over the sun, and then back down to the south. I don't know of too many that have come down from the north and out through the north that have been naked eye visible. It's actually kind of interesting if you plot the path, because of the Earth's orbit around the sun. It makes the comet makes this spiral in the sky as it moves away, because of the way the comet is orbiting around the sun within the solar system. It isn't planar with the planets. It's basically almost perpendicular in some respects to that orbital plane in a lot of cases.
Hey, Derek, Don is asking if we know how big is Comet Swan.
I do not know the answer to that question. I actually haven't done a lot of reading about Comet Swan, but I hope to change that over the next couple of days, because I want to try and get out and see it myself, and hopefully maybe even get a picture of it. Probably not like the picture that Scott showed us, but I would like to get at least one picture of it.
Absolutely. I know Scott's planning on trying to go down every night that's clear anyway.
Yeah. So, I don't know, Gavin, any thoughts on comets viewing? I know
I was just going to point out, is this a website that you're looking at, or is that a program you downloaded to your computer? So that our viewers can get in on that?
That is the SkyLive Planetarium website. I usually use Stellarium, but I don't have it installed on this computer, so I had to come up with something quick.
So you just Google for the SkyLive, you should be able to pull that up.
The skylive.com /planetarium.
Yeah, the Sky is actually a great website for information about comets as well.
Yeah, it looks like they have another section on like just talking about objects as well. So pretty good. I don't know if I got any more to say about the comets.
So there's another comet too that just came into view. So there's a comet called C2020 U6 Lemon. And this comet is currently in the constellation Lepus, which is right next to Canis Major, kind of under Orion. So it's not, again, this is Southern Hemisphere, a better place to see it right now, but Comet Lemon, or Comet U6 Lemon, has also experienced an outburst, just like Comet Swan did. And this is made it substantially brighter than what we were expecting it to be. And we're hopeful that when it gets into the Northern Hemisphere skies, it may become naked eye visible as well. And that would be awesome if we had two naked eye visible comets at the same time.
I'm navigating here through the ground to see if I can find Orion. But yeah, it's Down here in the ground. Again,
It
the
is.
Southern Hemisphere always seems to get the better deal. Yeah, there's Orion through the grounds, and you've got Canis Major right here.
The very floral view.
Yeah, look at that. You got some nice grass. Oh, man. Yep, it's Friday after a very long week. So, and then this is, I just saw it a second ago. Oh, well. Yeah.
Now,
Kind of got lost.
I wanted to mention real quick that, you guys have been tuning in every week, and we want to get feedback from you guys. We want suggestions. What are some of the things that you would like to see us do? Now, we have very limited amount of actual live observing we've done, and it's largely because of the weather that we've been experiencing. That will eventually clear up, but we want to know what you guys want us to do. As far as opening at Frosty Drew, I've been in communication with as many people as I can be to figure out what's going on as we reopen Rhode Island. And as of right now, it looks like it's going to be difficult to host any kind of stargazing nights at Frosty Drew until after Memorial Day weekend, unfortunately. Now, that could change. We don't know for sure. I mean, everything's changing so quickly right now. But if that is the case, then this is how we're going to be bringing the cosmos to you for the next few weeks. Now, we're very anxious to open back up. We miss seeing you guys. We miss looking at your faces in the dark. And though we do look forward to this is definitely not the same. But we want to make sure that we're doing what you guys want. So please, astronomer@frostydrew.org. Submit to us not only your questions, but also submit to us suggestions or ideas that you may have that you would like to see us do, or things you'd like to see us talk about. Because we could talk all night about astronomy and the cosmos, but we can also talk a lot about the devices that we've created. We have everyone on the team has got an engineering background, and we've made a lot of really cool devices that allow us to do what we do. And there's a lot of gearheads out there that can really get into that. And I said it earlier too, and for anyone who just tuned in, we want to start taking questions during the week for you guys, questions that we will pose over the chat or over our discussion on that next Friday. So submit your questions to astronomer@frostydrew.org as well, and we'll answer your questions on the air. Now, take a look at Derek real quick. So Derek is sitting in an observatory in his yard that he built.
Gavin helped.
And Gavin helped him out. And along the way, we've heard a lot of really great stories about Derek's observatory, like leaks and vermin and stuff like that. But
yep, there was the great USB cable massacre of 2017.
But that is an impressive observatory that Derek built. And perhaps one week we can do a showcase of his observatory a little bit and kind of learn a little bit about how they did this and how you guys could do it if you wanted it at home, if you're, that level of geek.
Yeah, it's pretty fun. I like building things. So this was just the thing to build on an unseasonably warm, what was it, January?
Yeah, it was over winter shutdown one year. We were just out there in light jackets, hammering away.
Yep. But the other thing I want to talk about was this is the year that we were that Saturn and Jupiter are going to be the stars of the summer sky. They are right next to each other, and they're going to be like that all year. So we really want to get out to Frosty Drew and show those off, because there is no telescope with a camera on it that can do justice to what you see with your eyeball on a planet when you look through a telescope.
At Frosty Drew, when we have the big telescope on Saturn, it's kind of funny the responses that you get from people in the room. A lot of times that you get people that are out and they're on a date, sometimes like a first date, and they got the coolness thing going, they're showing off for each other, and they come up to the telescope, they take a look at Saturn, and for about maybe 10 seconds, the coolness just drops off and the inner geek comes out. because it's such a surprise. It's so unexpected. I mean, you knew you were going to see something, but you didn't think you were going to see the rings and the storms and the equatorial bands and the moons and the gaps in the rings. And a lot of people think the view is fake. Like, they'll be like, what, do you got a sticker on the lens? It really is this amazing, the view.
And I have too many trees to be able to see something this far south in the sky. I have to wait for winter skies to be able to see these planets, which is another 5 years for Jupiter and another 13 years for Saturn. Yeah, too long.
And on the solstice, the winter solstice, December 21st, Saturn and Jupiter are going to be so close to each other, visibly, so in conjunction, that in a telescope, not only will you see both of the planets together, but it'll look like their moons are mixing together.
Wow.
We plan on hosting a special event that night for that conjunction. So
the summer solstice, right?
No, it's the winter solstice, actually.
Really?
Yeah, it's definitely a little ways away.
Yeah.
No less awesome.
Crazy.
And I've been showing this the last couple of weeks, and I'm going to show it again real quick. This is from April 24th in the morning at Frosty Drew this year. And this is the Milky Way rising up over the dome. And this is the best, and this is another sad thing about this whole lockdown, is that this is the best time of the year right now to see the Milky Way at Frosty Drew. This is our peak Milky Way viewing season, because in the morning you get the Milky Way like this. Now, granted, when you're standing out there, you're not going to see it like this. I mean, you're not going to see the colors. The sky isn't going to look so bright to you. But what you will notice is you'll see the same structures and the same features that you see in the image. You'll notice these dark dust lanes over in here, like the Pipe Nebula. You'll notice the bulge of the galactic nucleus. You can see this little dust lane here called the Dark River to Antares. You'll see this very large dust lane here called the Great Rift. And you'll notice that all these little areas here that are kind of like little colorful here, they'll appear as just little bright spots in your view. And when you look at it, you can clearly see the same thing, just not in color. Now, we took this image during the Lyrid meteor shower peak, which is usually pretty weak. We usually don't see many meteors. But this year, we saw dozens of Lyrid meteors. It was really quite fantastic. And though I wasn't setting out to capture any Lyrid meteors, I actually captured two. There's one right here, and then there's another one right here. This is the Milky Way galactic nucleus, and all these dark regions here in this dark wispiness, these are all dust lanes. Most of this is just cold hydrogen gas that sits along the galactic plane. All these red regions you see in here, these are all star-forming nebulae. And you got some other regions in here of what's a little more blues, and these regions are sections of younger stars. They're not necessarily clusters of stars. They're groupings of stars. And this here is Jupiter rising, and this over here is Saturn, right to the left. Another thing to note too is we were talking about Saturn and Jupiter. We also have Mars this year. Mars is every other year that we get to see Mars in the night sky. And opposition, which is the best time to observe Mars, and that's when Mars ends up on the opposite side of Earth than the Sun. It's consequently right around our closest time to Mars too. That's the best time to look at it. And that's happening this year. So Mars is going to be another really great object to be looking at. So that's another reason we want to open back up, because when Mars goes through the opposition period and you take a look, you get about a month or two where you can see the Polynesia on Mars. You can see the ice caps in the polar regions. You can see the canyons and the volcanoes, those huge volcanoes on Mars. You can see clouds in the atmosphere. You can see dust storms. It's really quite fabulous. And though the telescope at Frosty Drew does an okay job, the telescope at LAD Observatory, our guest speaker last week, Bob Horton, he's the manager of LAD Observatory. I work at Observatory. That old refractor in there, that 12-inch refractor, is amazing at looking at Mars. And there was one year we looked at Mars during opposition, and I felt like I was looking at the moon. There was just so much detail in the view. So hopefully we can get things rolling again. And if LAD, like Frosty Drew, gets to open back up, then you'll be able to see Mars this summer. And I highly encourage it. Got anything, Gavin?
Not against, amazing specters of planets together in the same eyepiece and Mars and all that. Going to be a good summer.
Let's see here. I have
definitely the year for planets.
I have a good view of. Actually, you know what? Here we go. Planets. So just this past week. So we're at home. We're on lockdown, and I got like this 3.8 terabit data store of images that I haven't even looked through yet. I collected the data, I brought it all home, I threw it up on the storage server, and then I just left it there, and I never got around to going through it. So I've been kind of thumbing through a lot of this stuff over the last couple of days, and I found a really great little image that I processed out. Now, this image is from last year. This is last August. And we shot this one night at Frosty Drew. This up real quick. And this is an image that I totally forgot that I even captured, but now I remember doing it, of this is the gibbous moon with Jupiter in conjunction. And if you look at Jupiter here, you can actually see all 4 of Jupiter's Galilean moons. And though this is a lower resolution version of the image, on the high resolution image, you can actually see the equatorial bands on Jupiter as well. And we captured this on a night that we had what we call the lunar lounge setup. In the summer at Frosty Drew, we'll take a telescope. Whenever the moon's up, we take a telescope, we put a camera in it, and then we get a projector, and we set it up on the outside wall of the Sky Theater and project a live view of the moon up on the wall. People can sit out there and get eaten by mosquitoes. So this was some of the data from one of those nights that we were doing the lunar lounge. And this really is a fabulous image. There's a lot to see here. I mean, you can just start seeing some of the color in the different regions of the moon. You got a little bit of the reds over here, and then you got a little bit more of the blues over here, and then you get just the grays. These blue regions you're looking at, these are areas that have higher deposits of titanium on the moon. These redder regions are areas where are a little more iron poor, a little less iron in those regions. And these are where these different colors come in. Now, when you look at the moon with your eye, you don't see these colors because they're very subtle. But the camera collecting enough photometric data, is what you call it, or photons over a period of time, is able to start to capture some of these subtle colors. You also have down here, you have the Tycho crater. Copernicus crater is right on the terminator here, right on that sunset line. Here's Plato crater. This is called the Sea of Serenity, Maria Serenitatis. This is Maria Tranquillitatis, the Sea of Tranquility. Right over here, you have Maria Crisium, the Sea of Crises. I mean, you got a lot going on here. So I wanted to just kind of put this out there that this is, even though we're at home and we kind of get cabin fever, we want to get out, this is a good time for us to start, looking through all that stuff that we've just been blowing off in the past because we just didn't have the time to do it, right?
Yeah, I've been deleting a lot of stuff because it was not very good.
There's not a lot of that too.
I have room for more stuff, which is good because that's always the question. Is like, where am I going to put this? Because it takes up a lot of space on your computer hard drive.
I think I have a problem with deleting any astronomical image data that I've captured for some reason, because I'll look at it and I'll be like, wow, I captured this like 11 years ago, and this is just the camera I use is just terrible, but I'm just going to save it because one day I might want it. And now I got like 3.8 terabits of junk.
Yeah, digital hoarding is definitely a problem.
Yes. But I know that there are a lot of really great images in there. I mean, just some of the other things I found. The really great image of the Rosette Nebula, which Gavin showed a couple weeks ago, one that he captured. And I'm going to start working on that this week. But I was also out just this past week at Frosty Drew doing a little bit of work with what we call the Row of Phaiki Cloud Complex. And in the Milky Way image that I had up before, I'll throw it back up really fast, is you can see this. So get it real fast here. That cloud complex is right over here. So here's the Milky Way. You got these dust lanes over here, and then you got a little bit of these colors over here. Now the bright star is Antares, but this is called the Row of Phaiki Cloud Complex. And I worked on collecting about 3 hours of images or exposure of just this region right here. Now I didn't have enough time to process it out before tonight, and I was really rushing to try to get it done, but I just didn't do it. But I will be putting it up next week, and I'm going to be showing. We post them on our Facebook too whenever they come out. So if you're on Facebook, follow us, and you'll get these updates as well. But this is definitely, with the low levels of pollution in the atmosphere right now, light pollution is down too. It's really awesome out there, but it's just there's nobody there. It's really dead and it's really quiet, and it's somewhat dystopian, just watching the swings in a playground in the distance swinging by themselves, just in the wind. Now, so we're down to 5 minutes. We have any images to put up? Anyone last requests or anything like that? Anybody have anything?
Scott, I just didn't know in the other image you had up with the moon and Jupiter, if you could zoom in on Jupiter a little bit, because I was noticing on the YouTube live one that everyone's seeing, it's kind of hard to see the moons.
Let's see here.
It's officially raining.
Yeah, I know. I've moved out of the rain. I was getting hit by it. Let me bring it back up real fast here. So this is the best I'm going to get right here, right about this magnification or this zoom. But I could post a higher res image next week to throw up onto the screen. But let me find some. So real quick, what do we have here?
Here we go. Let's see if this one. This is a stack of Jupiter I did a while ago. Might be enjoyed.
Yeah, let's see it.
I haven't tried to do planetary in a long time, but where are we going?
Like you hear us talking about planetary and deep sky, and these are all different imaging sessions that we do, but they're very different. Imaging planets is substantially different than imaging deep sky, and it gets tricky sometimes. I mean, there's a lot of work that goes into it.
Yeah, with planetary imaging, you end up taking video and then taking each frame of the video and running it through a program that measures how sharp each frame is, and then it ranks the frames by sharpness, and then you select, the top 10,000 frames, and then you stack them through a program or a piece of software that attempts to align all of those video frames, and then you try and come up with an image like this. And this one's probably my best shot of Jupiter that I got many years ago. But I really enjoy it because it is a perfect pearl layout of the Galilean moons with Jupiter centered in that. And you can see the equatorial bands. I just think it's kind of a really nice composition. And I found it when I was digging through my archives of images, and I was like, oh, I thought I'd lost this image because I had it on my cell phone, and that cell phone corrupted the SD card, and I was like, I don't know where the original is. Oh, I found the original, so I was pretty happy.
Huh. That's a great image, though, Derek. I love it. You can see the equatorial bands on Jupiter as well. So now, when Derek was talking too about capturing frames as a video, the reason we do that is because, if you've looked through a telescope before, when you're watching our videos of Venus, you notice that there's a lot of waviness in the view. The object looks like you're looking at it, it's either on fire or you're looking at it underwater. because it's constantly distorting. And this is happening because of Earth's atmosphere. And we call this atmospheric dispersion. And if you try to do a long exposure on the planets, it's just going to be a blurry image when you're done because it's constantly going in and out of focus. So the idea is to capture frames really fast. You know, like if you can, like 100 frames per second or higher. And if you can capture at that rate, then you're going to capture a certain amount of images or frames where the object is perfectly in focus. And the idea is to then, like Derek said, evaluate your entire collection of frames and only keep the frames that are sharp and throw the rest away. And that's why we do it with the video. That's not how we do deep sky. That's not how we do most of the other images we show you, but from a planetary perspective, that's how you got to do it. So,
and I actually did this with a modified webcam. I ripped the bullnose off of the webcam and glued what's called a T-ring, which is basically a threaded ring that can be used to attach equipment to telescopes. So Scott was talking about some of the homebrew equipment that we've got. That was one of them.
Yeah, that's creative. I mean, gotta love it. So we are now at the end of our session. So one, I wanted to say thank you for joining us tonight. You know, this is us bringing the cosmos to you, from our home to your home. We look forward to this every week because it's a chance for us to connect with you guys. And we're happy that you've been able to join us. As I said earlier, if you have questions that you would like us to address or pose in our next live event, which is next Friday, then please send them to astronomer@frostydrew.org, and we will answer your questions over the air. Additionally, if you have suggestions or requests or ideas that you would like to see us do, then submit those as well to astronomer@frostydrew.org, and we'll do our best to try to show you guys what you want to see and try to do what you guys want to do. And until we can open up at Frosty Drew again, we will continue to do this every week. And we also want to note a special shout out to everybody who has donated to us during these events. I mean, it's helping us a lot. It's helping us get through this difficult time when we're not open. And it's giving us the ability to not only stay open, but to plan for when we are able to reopen. So if you had a great night tonight, if you learned anything of value, or you just enjoy what we're doing, then please visit us on the web at frostydrew.org/donate.php and make a donation. Anything you can do helps. I mean, we love you for it, and we're awesome because of you guys. So we'll see you guys next week, and we look forward to seeing anything that you send us via email. So have a great night. All right, we're just about done. I'm watching right now. And it's ended. It's